Hello, everyone, and welcome. Today, we're diving into a topic that's genuinely set to redefine our technological future, 2D materials. Now, this isn't just some far-off science experiment. It's a critical, strategic frontier, and it's especially important for India. So let's get right into it.
To get us started, I want you to think about this question. What are we talking about here? Something that's just a single atom thick, so thin it's practically two-dimensional, and yet it's stronger than steel by a factor of 200. The answer, of course, is a 2D material. So what exactly are they? For your exams, here's the core definition you need to lock in. 2D materials are crystalline substances that are just one to a few atomic layers thick. It's this incredible thinness that gives them these mind-bending properties. And the two big names you absolutely have to know are graphene, the most famous one, and a whole class of materials called transition metal Dichalcogenides, or TMDCs for short.
So here's our roadmap for this explainer. We're going to start with the basics at the atomic frontier, then we'll trace the timeline of discovery, we'll explore the two worlds of application, understand the huge global supremacy race, and finally bring it all home to India's strategic mission.
First up, the atomic frontier. Look, before we can talk about the high-level strategy and the geopolitics of it all, we really need to build a solid foundation. We need to understand why these materials are so revolutionary in the first place.
So why all the excitement? Why are these materials such a game changer? Well, it really boils down to four incredible properties. First, their exceptional conductivity. Graphene, for instance, conducts electricity even better than copper. Second, their unbelievable mechanical strength and flexibility. You can stretch some of these up to 20% without them breaking. Third, and this is absolutely vital for the future of computing, TMDCs offer breakthrough semiconductor performance, which could let us finally move beyond the physical limits of silicon. And last but not least, they have a quantum advantage, making them critical for building the next generation of quantum computers.
Okay, let's move on to our timeline. What's really striking here is the sheer speed of innovation. This isn't a technology that's taken a century to develop. Its rise has been absolutely meteoric.
So the theory actually started way back in 1947, but the real revolution kicked off in 2004. That's when graphene was first isolated, and famously, it was done with just a piece of Scotch tape. That discovery won a Nobel Prize. And after that, things just took off. By 2011, we had semiconducting TMDCs on the scene. By 2022, we could grow them on an industry-standard 300mm wafer. And get this, by 2025, the first microprocessors made entirely from 2D materials were announced. Think about that. From a piece of tape to a full computer chip in just over 20 years. For comparison, silicon took more than 5 decades to get there.
All right, now for a really critical distinction, especially for those of you preparing for exams. You have to understand that not all 2D materials are used in the same way. We need to separate the super high-tech, single-layer forms from the more industrial, bulk forms. They are essentially two completely different worlds of application.
First, let's talk about the high-tech frontier. This is where you use a single perfect atomic layer, what we call a monolayer. This is what opens up the future of computing. We're talking next-gen semiconductors, quantum computing, optoelectronics for things like advanced sensors, neuromorphic computing, which is designing chips that mimic the human brain, and heterogeneous integration for stacking different chip materials together. Now, to help you remember that for an exam, you can just think of the acronym SQON.
Then, on the other hand, you have what we call the bulk forms. Now, these are basically flakes or powders of 2D materials that you mix into other things. Think of them as industrial workhorses. They're used to create stronger composites, better batteries and supercapacitors, advanced water filters, and super durable coatings. This is all about enhancing the industries we already have today.
And this table right here illustrates that difference perfectly. This is a high-yield area, so it's definitely worth a closer look. Monolayer is for high-tech stuff like semiconductors, targeting foundries and AI chip makers. Its key property is its tunable band gap. Bulk, on the other hand, is for industrial applications like composites, targeting battery makers and the construction industry. Its key property is its sheer mechanical strength. Understanding this distinction is absolutely key to seeing the whole picture. So, we understand the science, we know the applications. But when something has this much incredible potential, it inevitably kicks off a fierce global competition. This isn't just about building better gadgets anymore. It's a high-stakes race for technological leadership. You could even call it the geopolitics of an atom.
And why is this race so incredibly intense? Well, the answer, as it often is, comes down to economics and strategy.
The projected market for just the semiconductor applications of 2D materials is estimated to be somewhere between $75 and $150 billion by 2035. That is a massive, massive prize. And the patent landscape gives us a really clear picture of this R&D competition. As you can see from this chart, China is an absolute dominant force here. They've filed over 10,000 patents in this space just between 2015 and 2023, far outpacing the US and South Korea. This isn't just research, it's a clear statement of strategic intent.
But this intense competition creates some very real vulnerabilities. For example, we're seeing the US use export controls on the advanced tools you need to manufacture these materials. And in response, China is controlling the export of critical raw materials like gallium and graphite. The big risk here is something called technological balkanization, a key term to remember, where innovation gets trapped behind national borders, which ultimately slows down progress for everyone.
And this brings us to the most important part of our discussion today, India's role in this global race. The situation right now presents a critical but also a rapidly closing window of opportunity for the nation to really establish itself as a leader in this field.
The stakes for India could not be higher. It's a classic fork in the road. On one side, you have this incredible opportunity to leapfrog directly into post-silicon leadership, build true self-reliance in critical technologies, and capture a huge share of a new industry. But the cost of inaction is just as stark. Permanent technological dependency, being vulnerable to global supply shocks, and a brain drain of our best scientific minds.
So what's the path forward? What's the game plan? Well, the recommendation is a very clear 5-point national strategy. This involves creating focused innovation hubs, prioritizing homegrown R&D, building better bridges to get technology from the lab to the market, forging smart international partnerships, and tying all of this in with existing national programs, like the India Semiconductor Mission.
All right, we have covered a lot of ground, so now let's condense everything down into the key takeaways. If you're studying, this is the part to really focus on. These are the most critical points you need to remember.
First, the core concepts. Remember the definition of 2D materials, with graphene and TMDCs as your key examples. You need to know their key properties, especially the tunable bandgaps of TMDCs. The monolayer versus bulk distinction is absolutely non-negotiable. You have to know it. And finally, understand the geopolitical landscape. It's a high-stakes race between China, the USA, and South Korea.
Next up, the key facts and figures. Graphene is 200 times stronger than steel. The timeline from discovery in 2004 to a microprocessor by 2025 is incredibly fast. The market size is projected to be huge, up to $150 billion. China is leading the patent race with over 10,000, and the 300mm wafer milestone was hit in 2022. These are the numbers you'll want to have ready.
And finally, let's recap India's mission. The #1 goal is technological sovereignty. The biggest risk is being completely locked out of the future of tech. And the strategy is that clear 5-point plan we discussed, focusing on innovation hubs, indigenous R&D, lab-to-market translation, global collaboration, and full integration with our national missions. I want to leave you with this really powerful quote from the source material. In today's global techno-industrial landscape, inaction is no longer a neutral stance. It is a strategic regression. I think that just captures the urgency of this perfectly. Standing still means you're actually moving backward.
And that brings us to our final, thought-provoking question. We all know that silicon is reaching its physical limits. So the question for all of us, and really for the nation, is this. Will a focused, mission mode push into 2D materials be the strategic masterstroke that redefines India's place in the global technology order? That's what we'll all be watching for. Thank you for joining this explainer.